Okay, in this video, we're going to start to make the connections to energy and power. And we've already talked about both of those topics, but we talked about them in terms of mechanical energy. So we talked about kinetic and potential, we talked about work, we even talked a little bit about elastic energy. And we've talked about the concept of power, the idea of how fast you're using energy or how fast energy is being used up. And so what we want to do now is we want to take those electrical properties, things like voltage or current or resistance, and we want to see if we can't use them as a way to calculate how much power is being produced by a circuit or by a particular element in a circuit, and then also how much energy that particular object is going to use. So in order to do that, let me remind you of the fact that we actually already have an equation for electrical energy. And this is why it was introduced in the previous topic on electrostatics, this idea of electric potential energy. And that formula for electric potential energy looks like this. E is equal to Q times delta V. So that is a form of electrical potential energy in the same way that the formula E is equal to mgh is a form of gravitational potential energy. This is the formula for electrical potential energy. Now the formula for power is E divided by T. So here's what we're going to do. We will be able to derive a formula which will involve electrical properties by just making a very simple substitution. All I'm going to do is, so this is the important thing, right? We're trying to find a formula for electrical power. So here's a formula for electrical energy, and electrical power is based on electrical energy. So we are going to make a little substitution to plug the Q times delta V in for E right here. And when we do that, we're going to end up with this equation, Q times delta V divided by T. But let me just remind you really quickly that this that's I, the current, right? The equation for current, this is really one of the reasons that I wanted to show you that equation. It's not the most important equation in the world, but it is the definition of electric current. And here it is hidden in this new equation that I derived by putting Q delta V for the electrical energy divided by T. If I combine these two guys together, I end up with I times V. So this gives us an equation for power that says P is equal to I times V. Very important equation because it allows us to start thinking about energy in electrical systems using only purely electrical properties like I and V. Now, what I would like to do is to remind you that R is equal to V over I. So there's actually a third electrical property that is not in this equation yet. And so all I want to do is I just would like to derive some alternate versions of this equation. So what I'm going to do is I'm going to show you two different versions of the equation, and the way that I'll get those equations is I'll combine the P equals IV equation, this new equation for electrical power, with the R equals V over I equation. And you'll see that we end up with several alternate versions, both of which will involve the variable R. So we're going to do it this way. So P is equal to I times V, as we just established in the previous calculation or previous derivation. And I'm going to solve this. Let's do first of all V. So I'm going to make a substitution in this equation. P is equal to I times V. I'm going to substitute V this version of the equation. So I'm going to do a little bit of algebra here before I write this. So if I were to get V by itself, all I would do is multiply by I, and that would say that V was equal to I times R. So since V is equal to I times R, I could make this substitution. And when I substitute that in, I'll end up with this. P is equal to I times the quantity I times R. So we can go ahead and combine these two together to get a second version of the equation that says that the electrical power can be calculated by using I squared times R. Second version of the power equation, but this time using I and R rather than I and V. So you have to imagine that if I can use I and V, I can use I and R. There must be some version of the equation that allows me to use V and R instead of using I at all. So in these two equations we use I, but it's not something that we can't get around. So let me rewrite this. P is equal to I times V. This time what I'd like to do is I want to solve this equation for I. So remember, if I'm going to multiply by I to move the I up here, I will divide by R, the R will move down over here, And I will end up with this equation that says that V is equal to, I'm sorry, we're solving for I is equal to V over R. So we'll do the same thing that we did in the previous derivation, except for this time we will substitute for I, and we'll end up with this equation. P is equal to V over R times the quantity V, or that is to say that P is equal to V squared over R. Okay, so three versions of the power equation using different combinations of the three primary electrical properties, which is V, I, and R. So I'm going to put all this together, and I'm doing that mainly so that I can show you what it's going to look like on the equation sheet or the data booklet, whatever you're allowed to use. It's not going to be listed as three separate equations. It'll be listed like this. It'll say that electrical power is equal to I times V, but it's also equal to I squared times R, and it's also equal to V squared over R. Now, we could solve any problem using only the P equals IV equation. It's not like we can't do it, but we'd have to do two steps. So we would, for example, let's say that I didn't have I and V, but I had R and I. Okay, well, I could certainly get this equation, but then I would have to calculate the V using the R equals V over I equation, and then I would substitute that in, and then I would solve for the power. So the purpose of having these alternate versions of the equation is that I don't have to do two steps. So instead of doing two steps, where I use the R equals V over I, and then I use the P equals IV equation, this has allowed me to already combine those together, so I don't need to go through these steps all over again. Three versions of the equation, depending on which of the two electrical properties that you have in any particular example. Now, the purpose of looking at electrical power is really to start thinking about energy. And the reason for that is because that is what you buy with electricity. You are buying energy. Now, I know oftentimes the electric company is called the electric company, or it's sometimes called the power company, but that is not the proper name for the company that you buy your electricity from, because they are not selling you electricity. What they are really selling you is energy. Now, the reason why they're called an electric company is because of how they deliver the energy to you. They deliver it through electricity. They use those little charge carriers, those electrons, to store energy and send that energy to you, could be miles and miles down the line. So in order to think about electrical energy, we have to kind of think about a new unit, because the unit of energy that we've been using, which is the joule, is actually a pretty small unit of energy. I mean, every human being, on average, uses more than about 8 million joules of energy just from the food that you consume each day. So a joule is not a very big unit of energy, and as you can imagine, your house takes a lot of energy. So it's kind of an inconvenient unit, because this is no exaggeration. You use probably in your house or in your apartment more than 1 billion joules per month just from your electric alone, just from the electric bill alone. So it's really kind of a unique thing. This unit of energy that we're going to derive right now is really only used for electricity. I mean, it could be used for other things, but it's, for whatever reason, it's really only used for electrical energy. So let me just real quick, let's remind ourselves that P is equal to E over T. So it's the amount of energy that you use per time or per second. And therefore, if we wanted to know how much energy an electrical device, like let's say a light bulb, for example, used, then we would say that E was equal to P times T. All I've done is I've just rearranged this equation so that I've solved for E. E is equal to P times T. But now what we're going to do is we're going to look at a new unit. A new unit of energy, and all we're going to do is we're going to swap out the usual units for energy. So in the equation, normally E would be equal to, so in this case that would be watts times seconds, and a watt is equal to a joule per second, and when I multiply that by seconds, the seconds will cancel, and I will end up with joules. So typically when we calculate energy, we want to make sure that our power is in watts, because a watt is a joule per second, and that we use in our time seconds, and that will produce units of joules, and that's perfectly acceptable. I mean, that really truly is the standard, the international standard for energy. But in the electrical world, it's too small. It's pitifully small. A joule is basically the amount of energy to lift a medium-sized apple by about 1 meter. It's not very much energy. It doesn't take a lot of effort to do something like that. So instead, we're going to do something slightly different. We're going to say that E is also equal to, but in this case, I want to use a bigger unit of power. So a watt is too small. So what I'm going to use is a kilowatt. And instead of using seconds, seconds is a very short period of time, I'm going to use a little longer period of time. I'm going to use the hour. So what we've done is, instead of, we will use kilowatts. Instead of seconds, we will use hours. Okay, now something kind of interesting is going to happen. Here, when we did watts times second, they turned into a whole new unit called joules, right? Which might have maybe kind of hidden inside the units here. But in this particular one, we aren't going to do anything. We're not going to make any kind of conversion. Nothing new is going to happen. When I multiply kilowatts times hours, I end up with the kilowatt hour. And that is pronounced kilowatt hour. You just run those all together, the kilowatt hour. Now, it would be very helpful to understand how many joules are in a kilowatt hour. How big exactly is a kilowatt hour? Super important. If I say kilowatts, that's power. But if I say kilowatt hours, that's energy, because now I have multiplied by time, and that's what you need to turn power into energy, is to multiply it by time. So let's do a quick conversion so you can get a sense of just how big of a unit of energy this is. So let's assume that we had 1 kilowatt hour. The first thing I want to convert is the kilowatt. So what I'm trying to do is I need to get to joules, and in order to get to joules, I need watts and seconds. So I need to change these two guys from watts to from kilowatts to watts, and from hours to second. So I'm going to put 1 kilowatt on the bottom so that I know those are going to cancel correctly, and on the top I'm going to put 1,000 watts. And then now we want to get rid of the hours, so the hours will come down to the bottom. They will cancel those hours, and there are 3,600 seconds in 1 hour. So I now have watts times seconds. That's exactly what I need to turn it into joules. And the answer is 3.6 times 10 to the 6th joules. Or that is to say that 1 kilowatt hour is equal to 3.6 times 10 to the 6th joules. That's 3.6 million joules. That's a lot of energy, but in my house, for example, I don't think I've ever seen our electric bill be below 400 kilowatt hours. Generally speaking, I would say my bill specifically doesn't usually go above 700 or 800 would be like the maximum number of kilowatt hours, but there have been 1 or 2 times where I have seen, either because it was just really hot and so we had to run the air conditioning a little bit more, I have seen times where it reached 1,000. So just think about that. That month where my house used 1,000 kilowatt hours, I used 3.6 billion joules of energy just in that month alone from the electric company. And they only charged me about $100 for that, again, almost 4 billion joules worth of energy. So the purpose of the kilowatt hour is to just make it more convenient. So instead of me saying in my on my electric bill that I used 3.6 billion joules, I would say I used 1,000 kilowatt hours. So just a bigger unit of energy, just more convenient for talking about, for example, like your monthly bill, because otherwise the amount that they're charging you for a joule, they'd have to charge you, something like less than 1,000th of 1 cent per joule. Just makes it a little more challenging unit to work with. So really only for this electrical topic are we going to use this new unit of kilowatt hours most of the time instead of joules. But let me show you how it works for both possible examples. So let's take a look at some example problems. There we go. Let's start with something small and then we'll look at something a little bit bigger. So something that uses batteries, and then we'll use something that uses the wall outlet, a little bit higher voltage. Different batteries are used for different electric cars or little remote control cars, but 9-volt batteries are one of the ones that you could use, or you could use 6 1.5 volt batteries, and then that would be the equivalent of a 9-volt battery. So right off the bat, I can see that I'm being given the voltage. Is the very first thing is the voltage. A 9-volt battery is used to power a remote control truck that draws a maximum current of 0.14 amps, and that 0.14 amps is going to be drawn when the car is at its maximum speed, or the truck, I should say, is at its maximum speed. So here is I. right? So the first question is to calculate the power. Well, that's going to be pretty easy, right? So P is equal to I times V. So in this case, the I is 0.14 amps. The V is 9 volts. And therefore, if we plug that into the calculator, we're going to get 0.14 times 9. That is equal to 1.26 watts. Not a lot. That's a pretty small amount of energy. Of course, the little battery-powered cars, they don't really require a lot of, a lot of energy, or a lot of power, I should say. So now the question is, how long can the truck run? Now, different batteries hold different amounts of energy, but let's assume, for argument's sake, that this battery only holds 378 joules of energy. How long will we be able to use this for? So in this case, we're not really using an electrical formula. We're using the equation that says that E is equal to P times T, or in this case, we would want to say that T was equal to E divided by P. The amount of energy divided by how fast we're using the energy, that's going to tell us how long that we're going to be able to leave this device on. So in this case, 378 joules, we are using it at 1.26 joules per second. And so therefore, when we plug that in, 378 divided by 1.26, that is 300 seconds. And just to put that into perspective, 300 seconds is about 5 minutes or so. So we'll be able to use that vehicle for about 5 minutes before it's going to run out of energy, and then we'll need to recharge that battery. So that's using the old system, the standard system of using watts and seconds. But let's take a look at an example where we're going to calculate things in a little bit different units, in this new unit that we've been talking about. So normally for a little remote control car, it doesn't really make sense to use kilowatt hours because they use such small amounts of energy. Kilowatt hours mostly going to be used for larger things. I would say a light bulb is probably on the smaller end of things that we might use kilowatt hours for, but your computers, your refrigerator, microwaves, any of these like larger devices, those are things where it makes sense to really measure in kilowatt hours. So let's first of all, let's calculate the power that is going to be dissipated or used by this light bulb, which has a resistance. So notice I didn't give you the current this time. I gave you the resistance and the voltage. So this light bulb has a resistance of 161 ohms when it is plugged into a wall outlet where it's going to be supplied with 110 volts of electric potential. So when I calculate the power, this time I have R and I have V. So I don't want to use the I times V equation. I want to use the V squared over R version of the equation. All I have to do is plug in those numbers now. 110 divided by 161. So that is, 110, my mistake, 110 squared divided by 161. And that gives us a power of about 75 watts. Okay, now I know when I go on to the next portion of the problem, I do want to do this in kilowatt hours. So this is going to be kind of inconvenient. I'm going to go ahead and convert right now so that I get this thing in kilowatts. So all I need to do to go from watts to kilowatts is to divide by 1,000. And in case you're not sure what to do, you just need to go through the formal conversion. So this says I want to put the watts on the bottom and I want to put the kilowatts on the top. I'm going to write those first. Since the kilowatt is the bigger one, the number goes on the bottom here. So 75 divided by 1,000, there are 1,000 watts in a kilowatt. That's going to turn this into kilowatts. So this will be 0.075 kilowatts. So I'm preparing for part B because I can see already that it's asking for energy in kilowatt hours, so it's going to be helpful to have this number put into kilowatts. Light bulbs don't use a huge amount of energy, so this bulb doesn't even come close to using a kilowatt. Whereas things like your microwave or even like a TVs in certain circumstances, they might actually use a kilowatt. For sure your microwave uses that much, and hair dryers also tend to use very large amounts of power. But other devices use a little bit less. So the question now is, how much energy in kilowatt hours, so I got the kilowatt part here, will it use in 1 month, which is, let's assume that a month is 30 days, if it's on for 10 hours per day? That's like a pretty typical thing. Like in my house, the light in the kitchen, for example, it's on for maybe like an hour or two in the morning, and then when everyone gets home from work and from school, maybe like around 4 or so, Then that light is on for, maybe another 8 hours or so that there's, on average, the light bulb in the kitchen in my house is on for about 10 hours, and it's on every day because we live there and we use the kitchen all the time. So what I need right now is I need to know what the time is. So I've already established that the power is equal to 0.075 kilowatts. And what I need right now is the time. So over here, I'm just gonna make a little quick side calculation. This says that I am going to use this for 30 days, and I'm gonna use it for 10 hours per day, so that gives me a total of 300 hours. Okay, so at this point now, the calculation is very easy, and I would really strongly encourage you, make the conversions beforehand. It's not like you can't do it after you've already made the calculation of the energy in joules. You could go ahead and make the conversion, but just much easier if you just calculate it in the first place in kilowatt hours. So now what I'm looking for is E. So I'm going to say that E is equal to P times T. That is going to be equal to 0.075 kilowatts times 300 hours to give me an energy of 0.075 times 300, 22.5. So over the course of this month, this light bulb will use 22.5 kilowatt hours. It doesn't have a lot of power, only 75 watts, but it's on for a long time. And energy is not just based on the power. It's not just how fast are you using the power, it's how long are you using the power. So you can have devices like microwaves that use have more than a kilowatt. Most microwaves are about 1 to 2 kilowatts, but how long are they on for? Maybe a couple minutes, right? So nowhere near an hour. So even though those devices use a lot of power, they don't use a lot of energy in your house because you don't have them on for very long. Whereas other devices like your TV, your refrigerator, your lights, those things are on all the time, and so that's where the bulk of your energy is coming from. So this one light bulb is going to produce 22.5 kilowatt hours in the course of 1 month, and that's just one light bulb in your house. Remember, in my house, my electric bill is usually between 400 and 800 kilowatt hours, and we must have, who knows how many light bulbs. There's probably at least 25 or 30 light bulbs, but most of our light bulbs don't use this much energy. We use the more efficient bulbs, and so they tend to use even a little bit less. But this gives you some idea of the concept of electrical power and then how to use that for electrical energy. And in one of the upcoming videos, we'll take a look at how do you figure out the cost of your electric bill. The first thing you'll do is you'll look to find out how many kilowatt hours, and then we'll look to figure out the price on your bill.